On Monday, we learned about digraph. Digraph means directed graph. And yeah, there are many applications. We can have one application like this scheduling. So in the scheduling, it means we have acts A and B. It means the task must be completed before task A must be completed before B can be started. So this can be a kind of curriculum in our department. Let's say if you are doing the computer programming at first, it will be helpful for doing the data structure. And if you are doing the data structure and computer programming, it will be helpful for the information system development and so on. There's one kind of specialized traversal algorithm. You already learned DFS, depth first search, and we can use this DFS with the directed graph, directed DFS. So we can specialize the traversal algorithms, DFS and BFS, to digraph by traversing edges only along their directions. In the directed DFS algorithm, then there will be 4 types of edges. If we are using the original DFS, we have only 2 discovery edges and back edges. But when we are using the directed, when we have a direction, there can be 4. We can discover the edges, we can have back edges, there can be forward edges, and there can be cross edges. So you can see this is discover edges, discover edges. This is discover edges, and then back edges. This is back edges, and then forward edges. This is forward edges, and then we have the cross edges. Okay. So there are 4 types of edges if we are using the directed DFS. And the directed DFS starting a vertex S determines the vertex reachable from S. So we want to know whether the vertex is reachable. The key point is reachable. Whether if I want to go from A, can I reach E or not? If I want to reach E, then there should be a path. So I can go to C and then I can go to E. So it is reachable. And yeah, you can also see from A to D, you can go A to C, C to D. Okay. So the concept is similar with DFS, but we have a directed edge. So in the direction or in the directed graph, we need to understand the concept of reachability. Reachability. Is there any way to reach a vertex from other vertex? DFS tree rooted at V. Rooted means we have a root or we want to start from a vertex and the vertex is reachable from V via directed paths. Directed paths means we have the edges which is a directed. So this is the direction. This is the direction. And if we want to check, is there any reachability from all the vertices? So this is the reachability. We can see that E is reachable from C and then A is reachable from E, and D is reachable from E. We can extend into this kind of tree. So we have like P. If we start from P, then it is reachable to D, it is reachable to F, it is reachable to C, and so on. Okay, so we can also reach E. From B to E, we can reach E through C. So if we have this kind of original directed graph, then we can have a tree like this, and we can also have a tree like this one. So there can be many trees. There is another term, we call it strong connectivity. Strong connectivity, it means each vertex can reach all other vertices. In the previous one, yeah, we just want to know whether a vertex V reachable or not. Okay. So we don't care about all the vertex, but we have the strong connectivity. It means each vertex can reach all other vertices. So I want to see if I need to reach all other vertex. If I start from A, then I need to know all the possibility to reach all vertex. In the strong connectivity algorithm, we can use DFS. First, we can fix a vertex V. So you can choose a vertex. Let's say I'm going to choose A. So if I choose A, then I can perform a DFS from vertex V in G. And if there is a W not visited, then print no. And then we can have G prime. Let's say the G prime is G with edges reverse. Do you know the meaning of reverse? So we want to see the opposite. Now we can see if it is starting from A, we have a direction from G to A. So we can have the reverse direction. It is the meaning by reverse. So the G prime is the reverse. You can see this one is toward C from A, and this is the reverse. This is also the reverse. This is also the reverse. And perform a DFS from V in G prime. Again, we will do the DFS with this G prime. If there is a W not visited, print no. Else, print yes. So it means if there is any W which is not visited, then it is not strong connectivity. So we can check all the possibility. If it is all possible connected, we need to build the G prime. If all are possible connected, then yes. Okay. The running time, if you are using DFS, we know that it is ON plus M. So the idea is only finding the not visited. We have the strongly connected components. In the strongly connected components means we have the maximal subgraph, maximal subgraph, such that its vertex can reach all other vertices in the subgraph. You still remember subgraph? So we have some partial, not all the vertices. If we deal with the strong connectivity, means we need to visit all vertex. But if in the strongly connected components, we can visit only the vertices in the subgraph. Can also be done in ON plus M time using DFS, but it's more complicated. It's similar to bicognitivity. So in this case, let's say if I want to split into two components, A, C, and G, and then I have another component. Let's say this is F, D, and B. So I want to make this is the first subgraph, and then this is the second subgraph. So this can be done with the DFS ON plus M. This can be done with ON plus M. But there will be more complication if we have a biconnectivity. Biconnectivity means if we want to find another connectivity between this node and this node in another subgraph. So if it is already set up with this subgraph and this subgraph, then yeah, the running time will be N plus M. There is another concept in the directed graph. We call it transitive closure. The transitive closure means given a digraph G, the transitive closure of G is the digraph G star. So G star means a new graph such that G star has the same vertices as G. So the number of vertices are the same. And then we have G has a directed path from U to V, and we can say U not equal to V. So it means there is no cycle. And G star has a directed edge from U to V. Okay, different. G has a directed path. You know path. So we can have like this one. This is a path, simple path. And the G star, we have a directed edge. The directed edge means we want to find some other possible edges throughout the vertex. So let's say this one. The transitive closure provides reachability information about a diagram. So if I have G like this one, I know that it is starting from A. Let's say I start from A, it goes to C, and it can go to D, and it can go to E. From B, we can go to B, we can go to C. So the transitive closure mentioned that there will be a reachable information. So from B, it is reachable, D is reachable from B. C is reachable from B. What about E? Yes, E is reachable from B because we have a directed edge from B to D and then D to E. So we make an edge from B to E. What about A to D? A to D, it is also reachable because I can go from A to C and then C to D. So I create an edge from A to D. What about A to E? Yeah, from A to E, I can go from A to C, C to D, D to E. So I can create an edge from A to E. So this is only the directed edge. And what about C to E? Okay, we can go from C, D, E. So we can create another directed edge from C to E. Because this is the G star. We want to find all the possible reachable information. The way to compute the transitive closure, we can perform the DFS starting at its vertex, and the complexity will be O n multiplied by n plus m. Because every vertex, we want to check the possible reachable information. So every vertex, we will perform another DFS. Alternatively, we can use dynamic programming, and we will use the Floyd-Warshall algorithm. So this is the idea. If there is a way to get from A to B, and we have another way from B to C, then there is a way to get from A to C. So if I can go from A to B, and then there is a way from B to C, then of course we can say there is a way if I want to go from A to C. The Floyd-Warshall transitive closure, we want to check all the vertices. So the first idea, we want to know how many vertices that we have. So it is from 1 until n. And then we need to consider the paths. The paths that use only vertices number 1, 2 until k as the intermediate vertices. So let's say if I have the I will check all the possible vertices I, j, and k, and then use only vertices number 1 until k at this edge if it is not already in. So we can have only the vertices that will be available with k. In this I until k, we can use only vertices number 1 until k minus 1. And for this one also, we can use only vertices number 1 until k minus 1. Maybe the idea can be seen in the example. We have this is the algorithm for the Floyd-Warshall. We check the number of vertices p1 until pn, and then we need to compute the digraph. The digraph means the G0, because we are going to check from the G0 until all possible k. So the input will be digraph G, and the output will be transitive closure G prime of G. When you do your team project, I always ask you, what is the goal? What is the output? So it means when you design your algorithm, there should be an output. So the two teams that I ask you to meet me, you cannot show the output. So that's why I want to meet you to help you. And yeah, we can search from all vertices, and then we want to put all the vertices into a variable v as vi, and then we can put all the vertices into the vi, and then we create a kind of graph G0. It is the subgraph, or it is the graph, the directed graph with particular edges that we will check from this algorithm. So in this algorithm, we are going to check for the k. K is a variable from 1 until n, and then let k, gk equals to the gk minus 1. So we have k, if it is starting from 1, then gk is the same with the gk minus 1. Gk minus 1, if k equals to 1, then it will be the same with the g0. And then we are going to check for every possible node. Here we will check the I, which is from I to n, but we are going to limit. So I will not be equal to k. And then we have another loop from j, j equals to 1 to n, and we again limit. So the j will not be equal to I. And then we need to check if the gk minus 1 are adjacent. So we have the vk, vi and vk. If it is adjacent, and vk and vj are adjacent, then we will check again this one. We will check again. If vi and vj are not adjacent, okay, so vi and vk and vj, they are adjacent. And if vi and vj, so vi, vk adjacent, vk, vj adjacent. But I want to know vi and vj. If it is not adjacent, then we will insert directed edge. So there will be a directed edge between vi and vj. And the directed edge, we also include the k. Okay. K means the number. So we will do this loop until we insert all the directed edges. This is the code. The closure we are going to copy from the G, and then we are making a list of the vertices, and then n will be the length of the vertices. So we will do the loop from 1, 0 until n. Yeah, this one is from 0 until n, and then this is also 0 until n. And then we need to make a limit. Okay? If I not equal to k, and then we want to find whether there is an edge between I and k. If there is an edge between I and k, then we will do loop on j. Again, we will check I is not equal to j, and j j is not equal to k. So we will check whether there is an edge between k and j. So the first is we have the I and k, and then we want to check whether there is an edge k and j. And then we want to check again if there is any edge in I and j. If there is no edge, then we will insert the edge I and j. Okay. So let's see just a simple example with this graph. This is a graph, a directed graph. There are 4 nodes, 1, 2, 3, and 4. And each of these nodes have the width. So we want to check we want to put the width into this matrix A0. Okay. So let's see if it is from 1 to 2. From 1 to 2, we have 3. Okay. And then what about from 1 to 4? 1 to 4, we have 5. From 2 to 1, we have 2. Okay. From 2 to 3, we cannot find any directed edge, so we put infinite. From 1 to 3, because it is still not reachable, we also put infinite, and so on. So if you can find the edge, then you will put the width. If you cannot find any directed edge, then you will put infinite. As we know before, we need to find the k, which is the intermediate vertex. Let k be the intermediate vertex in the shortest path from source to destination. So in this step, k is the first vertex, and aij is filled with aik plus akj. And then if this one is satisfied, aij is greater than aik plus akj. So this is the property also in the Floyd-Warshall algorithm, because I want to know ik, and then I have kj. If I want to know the ij, if I want to connect with the directed edge for ij, of course, there should be an edge from here, and then there should be an edge here, and the distance between I and j will be greater than this plus this one. So that's the constraint. That is, if the direct distance from the source to destination is greater than the path through the vertex k, then the cell is filled with the aik plus akj. Can you understand this one? So if it is satisfied, then I will make the cost or the distance between source to the destination, which is not covered, or if there is no directed edge, then it will be aik plus akj. Now let's see if I'm going to start from 1. Maybe here. So I'm going to make k equals to I. K equals to 1. Okay. So I'm going to make k equals to 1. So the I, so this is the number, the vertex. Okay? We can have vertex 1, 2, 3, and 4. The vertex j, it can be also 1, 2, 3, and 4. But as we know, I cannot be the same with j and cannot be the same with k. So all should be different. Then I can have k if it is 1. So I can put the a ik. It means a 2 and 1 plus a aj, which is a 1 and 3. And then I want to check what is the result if we have the a 2, 3. Okay. What is a 2, 1? A 2, 1, it is 2. What is a 1, 3? 1, 3, it is infinite. Okay. But I want to know what is a 2, 3. Okay. A 2, 3. Yeah, if you can see from this one, 2, 3. Okay. We have this. We can go. Let's say if I want to go from 1. Okay. You can go 2, 3. It is, if it is 2 to 1, 2, 1 for 4, 5, and then 4 to 3, 2. So the possible distance, if I want to go from 2 to 3, is 9. This one is greater than 2 plus infinite. Yeah, in the case of the infinite here, because we do not know the value, yeah, I just put the infinite. But actually, we can just assume that it is the first time for the 0, because I'm not sure about this value. So we can just omit this one, because there is no directed edge from 1 to 3. Okay. So 2 is smaller than 9. Okay. So we can later find the distance after we have another iteration. And then after we have this kij, so the j will be checked again. But we have another condition. I not equal to j, not equal to k. So we keep the k, we keep the I, and then we move the j. So we have this one, a21 plus a14. A21, it is 2, and then a14, it is 5. But we will check a24, there is a directed edge, 4. Okay. Okay, yeah, at this stage, we can just say that the condition for making this 4 is not fulfilled, but we can just put the distance 4, because we can find this one. We have the directed edge. Okay. So we do not need to make a new edge between 2 and 4. And yeah, let me just have one more. Let's say this one. We have 3, 1 plus 1, 2. 3, 1, 3, 1. We have no directed edge. So let's say this is just infinite. Okay. In this infinite, we don't have any value. Plus 3. Plus 3, it is 1 to 2. It is 3. But what about the 3, 2? Oh, 3, 2, we have a directed edge. Okay. Then we just put 1 for the 3 and 2. We do not need to make a new edge because there is a directed edge. And so on. So you need to check all the possible combination with the information in this graph. If it is satisfied, then you can make a new edge. If it does not satisfy, then you can use the original edge. So this will be repeated. This will be the iteration for k equals to 1. So you will do for all k equals to 1, and the combination will be 2 and 3, 2 and 4, 3 and 2, 3 and 4, and then 4 and 2, and then 4 and 3. In the iteration 2, we will start with the k equals to 2. And then we will check the 1 and 3, 1 and 4. And then we will do the same with k equals to 2, k equals 3, and then j equals to 1. So 2, 3, and 4. We have 2 and 4 and 1, and then 2, 4, and 3. So after we find this one, then again we will check with the k equals to 3. And then again check with k equals to 4. If you have 1 until 3, it will be enough to check for all the possibility, because it will be until the n. If it is until the n, usually we have the n minus 1. We have n minus 1, and it will be fine to make the new transitive closure matrix. So the final one, we can have the A for, okay, I don't put the note for, okay. And this will be the final matrix. This will be the final matrix after we have the Floyd-Warshall algorithm. So this is the distance. Okay. This is not only finding the new edge, but this is finding the distance based on this graph. Okay, that's the way to do with the Floyd-Warshall with the weight in the directed graph. Let's have a break. I will continue after the break.